Today's video is on a Krebs cycle. So Krebs cycle is the third stage of aerobic respiration. And so I recommend, if you haven't looked at the first two stages of respiration, you go watch my two previous videos on the first and second stages, which is glycolysis and the link reaction. So the Krebs cycle is the third stage of aerobic respiration after glycolysis and the link reaction. So jumping straight in with the first step of Krebs cycle, which is combining. So we start with acetyl coenzyme A. So acetyl coenzyme A is the product from our link reaction. So in glycolysis, the first stage of respiration, we produce pyruvate. And then pyruvate goes on to, in the link reaction, be converted into our acetyl coenzyme A in the matrix of the mitochondria. So we want to combine our acetyl coenzyme A with a 4-carbon molecule that is already in the matrix of the mitochondria. So we've produced our acetyl coenzyme A in the matrix, and now we want to combine it with a 4-carbon molecule already in the matrix of the mitochondria. And this 4-carbon molecule is called oxaloacetate. And this is extra information that you don't need to know. However, I do recommend that you learn it because a 4-carbon molecule is very vague, as this could be any 4-carbon molecule. So we want to combine our oxaloacetate and our acetyl coenzyme A in the matrix of our mitochondria. And so this is a 4-carbon molecule plus a 2-carbon molecule. So we're going to be getting a 6-carbon molecule, which is called citrate, also known as citric acid. So we have our oxaloacetate plus our acetyl coenzyme A, and this forms our citrate. The second stage is oxidation. So our citrate, our 6-carbon molecule, loses hydrogens, and losing hydrogen is oxidation. So our citrate is oxidized by losing hydrogens, and these hydrogen atoms that our citrate has lost go on to reduce 3 NADs and 1 FAD. So our NAD is being reduced to reduced NAD, and our FAD is being reduced to reduced FAD. So reduction, or being reduced, is gaining of hydrogen. So our citrate is oxidized by losing hydrogen, and our NAD and FAD are being reduced because they're gaining the hydrogens that this citrate has lost, producing reduced NAD and reduced FAD. Then the third step is about carbon dioxide. So, as this is a cycle, our product and reactant will be the same. So we're starting with this oxaloacetate, our 4-carbon molecule. So we can see that we want to regenerate a 4-carbon molecule because we started and end with this molecule. But if we look at the molecule we have at the moment, our citrate, it is a 6-carbon molecule. So we know we have to lose 2 of these carbons somehow to be able to regenerate our oxaloacetate so we can continue the cycle. So we know that we have to lose 2 carbon dioxide molecules. So we're losing our 2 carbon dioxide molecules, allowing us to have another 4-carbon molecule so that the cycle can continue. So our oxidized citrate is now going to lose 2 carbon dioxide. And then the last stage of Krebs cycle is substrate level phosphorylation. So far we've seen that our oxaloacetate and our acetyl coenzyme A have combined to form our citrate. Our citrate is oxidized, so it loses hydrogen to reduce NAD and FAD, and we have also lost 2 carbon dioxide. So now we're going on to substrate level phosphorylation, which is when a molecule directly transfers a phosphate group to an ADP molecule. So another molecule gives up its phosphate group to an ADP. So our phosphorylation of our ADP, we know, produces ATP, because ADP plus a phosphate is ATP. So via our substrate level phosphorylation, our ADP is phosphorylated to form an ATP molecule. And that means with our loss of hydrogens, our loss of carbon dioxide, and our substrate level phosphorylation, our citrate is eventually able to reform our oxaloacetate so the Krebs cycle can continue. So what are our overall outputs and inputs of the Krebs cycle? So it's important to note that per glucose molecule, 2 acetyl coenzyme A's are produced. So this is because in glycolysis, we have 2 pyruvate molecules produced per glucose, and in the link reaction, each pyruvate molecule goes on to form an acetyl coenzyme A. So for one glucose molecule, we have 2 acetyl coenzyme A's. And as one acetyl coenzyme A is enough to form a full Krebs cycle, that means that per glucose molecule, as we have 2 acetyl coenzyme A's, we are completing 2 full Krebs cycles per glucose molecule. So this is a table that summarizes. So our overall inputs are 2 acetyl coenzyme A's from our 2 pyruvates from our 1 glucose. And this will combine with our oxaloacetate. Another input is our 6 NADs, and this is 3 NAD per Krebs cycle because we need to be able to reduce an NAD. We have 2 FADs, 1 FAD per oxaloacetyl coenzyme A per Krebs cycle because we need to be able to reduce our FAD. And we have 2 ADP because we need to be able to phosphorylate our ADP to form our ATP. So it's 1 ADP per Krebs cycle. And our overall output is 4 carbon dioxide because we needed to lose 2 carbons to be able to regenerate our oxaloacetate. So 2 carbon dioxides per Krebs cycle. And we have 6 reduced NAD and 2 reduced FAD because we've reduced our 6 NAD and 2 FAD. And then we have our 2 ATP produced because we have phosphorylated our 2 ADP, 1 ATP produced per Krebs cycle. And our overall outputs are very important because our reduced NAD and reduced FAD are going on to oxidative phosphorylation, the last stage of respiration. And these are very important energy carriers in our oxidative phosphorylation. They go on to release electrons to the electron transport chain. So our entire Krebs cycle, the majority of its importance in respiration is to produce these reduced NAD and reduced FAD for the next stage.